Good morning, everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm your host for today's session. Before we get started, I wanted to touch on a few housekeeping details. Everyone attending today's session will receive by email an attendance certificate that most people use to substantiate their extended education credits. We encourage you during the course of the presentation to utilize the question entry block on the GoToWebinar control pane, and we'll try to answer as many questions as we can as time allows. And then we're recording the session, and it will be posted to the EasyPower website for future viewing, probably by early next week. Now, as we're in the habit of doing, I'd like to start the presentation or start the session before I hand this controls over to Dr. Tao Yang, to run a couple of poll questions. So the first poll question is, why does IEEE 1584 2018 version recommend a dynamic assessment of arcing faults for instant energy calculation? So again, there's no obligation or liability, but we'd appreciate some feedback if you would. Indicate your choice or guess or preference. And there are a lot of people indicating an interest in this topic because it is an interesting solution to the arc flash methodology. So it looks like we're about halfway to a form. Let's give this another 10 seconds. All right. Looks good. Here's how people have weighed in. Interesting. So the response I was looking for is the current changing over the time of the fault duration, which is an interesting prospect as far as the complication in doing the calculation. So that's what the focus is going to be today. And then the second question is, in your arc flash studies, how often do you use the 2-second rule? And again, the same conditions, no obligation or liability. It's strictly just some feedback that I personally am curious to see, because it's an area where there's a lot of discussion of the implications of what this utilizing the 2-second rule can do either for you or against you. So let's give this another 10 seconds. We're close to a quorum. We do appreciate your attendance today and your support of the EasyPower webinar series. So here's how people have weighed in on this one. Interesting. Those of you that aren't sure what the 2-second rule is, I'd encourage you to download from the website the Practical Solution Guide to Arc Flash Calculations, or attend one of our Arc Flash presentations, because it is an interesting topic of discussion, and the way it's implemented is strictly dependent upon your assessment of the effect on your equipment. So it's a good thing to pay attention to. Thank you for participating. And now, if you give me a second, I'd like to turn the presentation over to Tao.
Okay, thank you very much, Jim. Just double check, Jim, can you see my screen?
It's not on the slideshow. It's just on the...
Yes.
Yes, I can see your screen.
Yes, okay. Thank you very much, Jim. I don't plan to play the slides because today's presentation, what I'm gonna do is that for the first, let's say, 10 to 20 minutes, I'm gonna briefly go through what is short circuit focus, what is dynamic stability focus, what's their own purpose. Then we will migrate to EasyPower. I'm gonna use existing EasyPower example case, which is the DS example-1.ez that everybody should have access to under your documents or EasyPower sample file folder. We will use that case to calculate arc flash using both short circuit focus and dynamic stability focus to understand what is the difference and what is the similarity of arc flash calculation using short circuit and using dynamic stability. And to the end, we'll see why sometimes we want to use dynamic stability to perform arc flash calculation instead of relying on short circuit only. Okay, so first of all, let's do some background or knowledge review of what is EasyPower arc flash calculation and what is the dynamic stability. So today's outline, we're going to first review what is dynamic stability. Then we're going to show an example of using that DS example-1 to show how to calculate short circuit and short circuit based arc flash. Then we will use dynamic stability to show how to use dynamic stability to calculate arc flash. And then we can compare the results, make sure that how do we interpret the controls or the options we have for those two different calculations, how to make the result consistent under different circumstances. And once there is a difference, how do we interpret them, why there is a difference, and why the difference is important to us. I believe it's already covered in the poll question, right? Especially the first poll question, dynamic stability represents the system dynamics, which means that it represents the changing of the arcing current, right? Throughout the whole process, instead of just use short circuit to represent a snapshot. Even though you are using integration method, you may be using subtransient, transient, or synchronous impedance to represent your generator contribution, right? In short circuit, but they are still discrete. However, in dynamic stability, it's continuous. So we're gonna see why they are important, how important are they, how much difference it will cause, etc. afterwards. So that's the outline of today's presentation. If you have any questions, feel free to ask. If I'm able to ask on the fly, I will definitely do that. If I cannot, we'll just follow up and see if we can provide you with any answer or solution to your question. Okay, now let's get started and let's review what is dynamic stability. Dynamic stability analyzes the system response to a disturbance, including a fault, right? The power system has a lot of disturbance. You turn on the switch, turn off the switch, you have a fault and then cleared, you have a fault or not cleared, etc. Everything continuous going on can be seen as a disturbance to the power system status quo in some way, right? So it will tell you what is the system continuous response to any disturbance, not discrete, right? So if you have a three-phase ground fault or single-phase ground fault happen to the system, what is the system continuous response given the current system operating condition before the fault has happened, right? Instead of discrete, which is what short circuit gives. And it will tell you the transition from one steady state to another steady state, if possible. There may be a chance that the system will become unstable, which means that you cannot transit from one steady state to another steady state. For instance, if you open a switch, right? And if you have let's say you have a fault and you have to open a switch to isolate the fault, there may be some other things going on, such as generator loss, right? Such as big motor loss, right? Those kind of situations. For a situation like that, it's very possible that you may get a power flow solution before and after fault cleared and those equipment got tripped. But in dynamic stability, it may tell you that's not going to happen. You will never reach steady state after the disturbance from the prior steady state. So that's what we need to do to perform dynamic stability analysis to say how the system dynamic performance give us or response give us and say if we are able to achieve steady state from one to another after disturbance, right? Those are very brief, I would say, sketch of the concept of dynamic stability. Obviously, it takes years of analysis and experience to become an expert in dynamic stability. I would say that as the most comprehensive software package that we have in EasyPower, and one of the most comprehensive studies in the power system. Okay, so after we know what is dynamic stability, we can go back to go to the root of the short circuit focus and say, how do we use short circuit to perform arc flash calculation? So what is the sequence of performing arc flash calculation using short circuit focus, right? First of all, we need to model the system correctly if we want to analyze the system response to disturbance, right? Which includes that we may have to retrieve or obtain the most accurate and correct subtransient, transient, and synchronous generator impedance according to ANSI standard. Obviously, if you're in IEC world, that's a different set of parameters, right? So let's take ANSI as an example. You need to know what is the subtransient. Remember, in short circuit focus, many people may not pay too much attention to that. Some of the experts know what's the terminology. In short circuits, all the subtransient, transient impedances are saturated impedance. Keep that in mind, okay? Because for many of the generators, if you have a fault, right, the generator manufacturer will always give you, if they are responsible, right, saturated and unsaturated subtransient impedance, right? So if you use dynamic stability, please use the unsaturated subtransient impedance and transient impedance. If you are using short circuit focus, you should use the saturated subtransient transient impedance. Keep that in mind. Why? Because dynamic stability model already included a saturation model, right? So when you enter the impedance for dynamic stability, always use the unsaturated. For short circuit, always use the saturated, right? So that's the first thing in your mind. Then we calculate the fault current. You build your network model, you build your generator model, then you apply a fault, right? And then I suppose you also have your relay system set up as well. So the fault current would become an arcing current, and due to those relay settings and breaker settings, right, you can know your fault duration. So once you know the arcing current, once you know the fault duration, that's where the arc flash energy comes out with the corresponding enclosure types configuration you have with the corresponding I would say other parameters we have to enter for the we have to use for the attribute 1584. We can find out what's my incident energy and also my PPE levels, etc., or our arc flash boundaries, etc., from arc flash calculation, right? So all those parameters and the processes are what we follow in the short circuit focus of calculating the arc flash. So as we discussed, it's a mimic of the system continuous response through the discrete time snapshot, which is part of the integration method. So instead of using one impedance to represent the whole process, because arc flash, the fault duration may last, let's say 40 seconds in some cases, right? If you only have overcurrent relay in your system, and if the fault is not severe enough, you may have a very long fault clearing time. So for the subtransient and transient impedance, they may not be applicable, so you have to use synchronous impedance calculation, right? So integration method will use all three of them, depends on what time frame that we have for the fault duration, and then mimic the system continuous response through this discrete time snapshots as much we can obtain as possible based on the short circuit calculation standard, right? So that's what we have known already for the short circuit calculation. And let's just switch to EasyPower using the dynamic stability example, which is DS example -1.dz and example. In this case, what we want to do first is to open the breaker BH-M-1 to isolate the motor from contribution. We'll talk about that, or we'll talk about why we need to do that later. And then we go to short circuit focus. And then we enable arc flash in the short circuit focus. Double click on the MCC 4.16 kV box. We will see what's the arc flash boundary and incident energy is for the given distance, right? Make sure I don't have any questions come so far. Okay. The question is, can we get the presentation slides after the meeting? Yes, of course. As Jim said, we will wrap up the recording and the presentation slides, etc., within a week, I suppose, right, Jim? After this presentation and post it on our website as usual. Okay, so I'm gonna check the questions from time to time when I transition from one section to another. So feel free to ask questions. Like I said, if I'm able to answer, I will answer as soon as possible. If the question needs some time for us to discuss, well, I will definitely follow up with you with the answers and solutions. Right. So let's just go to EasyPower. If you want, you can play with me together just to get a I would say clear idea, a better idea about what we're doing, get a direct sense of what we're doing. That's okay if you just watch the show as well. So let's just go to EasyPower, launch EasyPower, and go to one lines, samples. There should be a ds example-1.dez file over there, which is part of our sample files, right? So let's open it. Now, let's open this breaker. Why we need to open this breaker? Look at the system configuration. The breaker opened is the generator, which means that there is only the utility source to be the source of providing short circuit, right? We want to open this breaker to isolate the fault current contribution from the motor. So our purpose here is to make sure that for a simple network, which is solely sourced by the utility, right? We are expecting the arc flash results at a bus in short circuit focus would be consistent with our dynamic stability focus obtained arc flash results, right? Because there is no dynamics. There is no dynamics involved anywhere in my current system after I open these breakers, right? So utility by itself is a steady-state source that it does not have dynamics. So no matter what, if we use short circuit or dynamic stability, we are supposed to get identical results. So this can help us give us some confidence that no matter short circuit or dynamic stability, as long as there is no dynamic response of the system, we should get the continuous and consistent results, right, across the board. Then the next example we're going to show is that after I include the motor and incorporate the generator dynamic stability model and recalculate the arc flash, we will see that what's the difference introduced by the dynamic stability model of the generator and motor contribution to the bus fault and the arc flash. Make sense? So let's just make sure EasyPower is doing the right thing, and then say what other things that dynamic stability EasyPower can do that the short circuit focus cannot do. So let's just go to the short circuit focus after we open this breaker, isolate the motor from contributing, right? To the short circuit. Remember to enable the arc flash, which means that display the arc flash results, enable arc flash. Double click on MCC 4.16 kV. This is the arc flash result. Your arc flash boundary is 139.8 inches, 29.9 cal per centimeter at 18 inches. That's your PPE level, right? Incident energy level, right? So let's record that. If you have a snapshot or if you have a screenshot capture tool, feel free to take a snapshot of that. I already did that because when I prepared the slides, I already take the shortcut to take a snapshot here, right? So 139.8 arc flash boundary, 29.9 calorie per centimeters at 18 inches, right? What else we can obtain from the short circuit? We know that the electrode configuration is vertical circuit breaker. We know that the bus bolted fault is 10.361 kiloampere, and the arc fault is 9.03 kiloamps. Those values should be able to help us validate if there is any problem, right? Troubleshoot if there is any problem. Trip time represents your, and opening time and arcing time, which is a combination of those two, represents your relay settings, right? Your incident energy is the results after you set up your working distance, etc., right? So black characters, remember, they're all black characters, means that we are using the average current method instead of the reduced method, right? So those are key options that we have to use or then stick to and be consistent across dynamic stability and short circuit to benchmark the results, right? So I will put this aside. We can come back to this, and let's go to dynamic stability focus, run the arc flash, and see what will happen. What's the step? So I think we don't have to go too much with this step because we already have reviewed that for the first page, that what is dynamic stability. Let's just go to the dynamic stability focus, look at the steps. Take the same case as an example, open the breaker, go to DS focus, enable arc flash, and choose IEEE 1584-2018 standard. Then double click the MCC. Okay. I already have opened the breaker, which is part of the prerequisites I did for before I enter the short circuit, right? Before I do that, let me just take a look at if there are any questions. Okay, no questions so far. Good. Now, breakers are open, right? Which is a steady state operating condition that I would like to have. Let's just go to stability. And let's go to DS options. That's where we can control the program. And that's where we can set up our configurations and also the display options, etc. So go to arc flash option. Remember, the simulation time step, I didn't change here. Some people like to use quarter cycle, but I just keep it half cycle because in my example here is irrelevant. Why? Because I have only one source, which is a steady state source. No matter how much simulation time step is, it's not going to change any of the dynamic behavior, right? So go to arc flash, choose the IEEE 1584-2018. All those options pops up. VCB, that's the option we choose in short circuit, right? Average, don't use reduce for this example, use average. But in the future, if you see the characters become purple, that means you need to use the reduced method, right? So for this example, because they are black, which means that the average current method is used, we should stick to the average arcing current method. Working distance 18, you can enter 0 to use short circuit working distance. There is not a problem with that. Maximum time is 1000 seconds, which means that we cover all the spectra. We don't use any shortcut or reduced time to shortcut the fault current, arcing current calculation, right? And use arc flash simulation for faults as the only. That is the option we enable the arc flash in calculation, right? So we click on OK. And then let's double click this MCC, see what will happen. On the plot, you can see that at a time equal to 1 second, right? This is where I started applying a fault, right? And then my dark blue curve is my per unit voltage. So after I apply a fault, the per unit voltage becomes changed from 1 per unit to 0.438 per unit because of the arcing impedance, right? And my arcing current goes up to 9,030 amps. Remember what we have here. Bus arcing fault is 9.03 kiloamps in short circuit, right? In dynamic stability, if you look at the red curve, put your cursor on it, or if you don't want to look at the curve, you can just browse this through and make sure that after 1 second, you can see the the third column, which is the fault current, arcing current column becomes 9.03 kiloamps. This is amps, so divide by 1,000. That's give you the 9 kiloamps, right? So you got the consistent arcing current between dynamic stability focus and short circuit focus, which is a good information, right? Now, how much time it takes for the upstream relay to trip? Either you can look at the curve to decide at what time the fault get isolated by upstream relay device, or look into the log file. That's where I like the most, to look into the log file to see what exactly has happened. So this state settled, that's your initialization. Apply a fault, simulate to 1 second, faulted the bus, simulation run to 6 seconds. Okay, those are the program information. Now relay pick up on overcurrent for all the upstream relays. And this RMCC 4.16 relay tripped on overcurrent, right? So it takes a relay 0.8917 to send the relay tripping signal to the breaker, right? And then at time equal to 0.9758 is 1 point, but 1 second is where I started applying the fault, right? So if you use this time minus the time I apply the fault, the total fault clearing time would be the relay fault clearing time plus the breaker fault clearing time, which is 0.9758 seconds. Remember what we had before. 0.974 seconds. That's the short circuit calculator relay clearing time, right? It's very close, right? 0.9758, 0.974. It's very close. So I would say the results are pretty consistent across the short circuit and dynamic stability, right? And keep going down. At the very end, it will show that your arc flash energy, let's just zoom it out to see the result clearer, right? Arc flash energy is 29.9 at 18 inches. Arc flash time 0.974 seconds. Arc flash boundary 139.8 inches. Bring the result back. What we have here, 139.8 arc flash boundary. 139.8. Okay, good match. 29.9 arc flash energy. 29.9 at 18 inches, at 18 inches. And then the next item, arc flash bus arcing fault. We already have verified it's 9.03 kiloamps across short circuit and dynamic stability, right? Opening time and arcing time and the trip time are all consistent. This opening time is 1.8917. I would say 1 millisecond round up error, right? So that's very accurate. Arcing time 974, arcing time 9758. But after the calculation of the integration time, remember our configuration showed that our integration time step for dynamic stability is 0.008, right? If you discount that back in, that will give you back 0.974 seconds because that's where exactly the arc fault ends, right? So we calculated consistent arc flash energy, arc flash time, and arc flash boundary across the board between short circuit and dynamic stability. Any questions so far? Let me see. No questions? Okay, wonderful. So this has helped us validate that if the system is only sourced by a device without any dynamic behavior or dynamic stability model, and if the fault current is always consistent across the whole simulation time, you get exactly the same result between short circuit and dynamic stability. So why do we need to use dynamic stability if everything is consistent, right? It takes us a lot of time and effort to set up the case, to run the events, and the results we see from the dynamic stability is from the logs. It's not even directly represented in a table that we can directly copy and paste, right? We have to post-process the message and get the result. Why we need to do that? The reason is because in power system, it is really rare that in your system, you have only one source, which does not have any dynamic stability model, and which does not cause any arcing current change during the arc flash time. It's always changing. Say you have a generator, the speed of the excitation system will determine how fast the fault current can ramp up and how fast it can decay, right? If you have a static excitation system, the fault current may be very consistent with your short circuit result. If you have a DC excitation system, which is very slow, then you may have a much smaller fault current. Eventually, you will have much longer fault clearing time, and which may lead to a much larger arc flash energy, right? Because of the relay settings, right? So everything is possible in stability simulation depends on different dynamic response of the generator and the motor, etc., whatsoever in your system. And that is why sometimes short circuit may not meet the needs of the arc flash calculation. Instead, we have to do the dirty work to use dynamic stability to model the system transient response, and then use dynamic stability to evaluate what is my arc flash energy closer to the real life instead of just using short circuit, right? So that is the purpose we have to use dynamic stability in many cases. Those are the options comparison. I believe we already have went through them from the example, because otherwise we can never get our result, right? If you don't set up the option right. So if you look at the arc flash hazard options from the database edit focus, and we have the arc flash options from dynamic stability control and options, make sure you check the enclosure, open air, arcing current, working distance, maximum time across the board. Make sure that those options are as desired. Many of us are very familiar with the arc flash hazard short circuit options, right? Same, we have dynamic stability options over there. What's your maximum time for different voltage? Here we have only one maximum time, which is okay. Depends on, usually this is not the value that we guess too much, as we sometimes this is a 2 second rule. 2 second rule is about, right, Jim? just a spoiler alert. That's something we have to consider from time to time. And also different voltage level for the short circuit calculation. The same apply for the dynamic stability. What's your default working distance, etc. We don't have any default. You have only one option, so we don't provide comprehensive calculation like short circuit, because you can run short circuit as many times as you want with different options to explore all the possibilities. Dynamic stability, you have to run stability run every time with a different option and summarize the result together. So integration method is a 1 cycle momentary, 8 cycle interrupting, and the rest 30 cycle, right? Those will be related to the different snapshot as we discussed. But the thing that if you look at dynamic stability, we will be using integration method, the dynamic stability instead of integration method, because automatically dynamic stability is a more detailed integration method to calculate the fault current and arc flash, right? So those are the options we have to be very careful and be very considerate when we perform the study. Now, we just already introduced why we use dynamic stability other than short circuit, right? We have to incorporate generator model, considering the real system motor model and the relay model, and the arcing current dynamics and the arc flash time due to the arcing current dynamics, due to the dynamic stability model involved. We can show some examples to show, we can use some examples to show that even for the same system, remember what we did was to open this breaker to exclude the contribution from the generator just now, what we can do is to open this breaker and close this breaker. So the system is sourced or is fed by the backup generator. Some people call it as backup, but it's just the generator, right? Get fed by the generator. And we can even incorporate the motor model into the consideration as well, right? To evaluate how the arcing current would change over time due to the stability model impact of the generator. So that's why we need to use dynamic stability on the short circuit. Let's take the DS example -1.easy as another example of adding dynamic model to Gen 1, which is this generator, right? And then let's add a motor model to M1, which is this motor that we just opened to isolate the contribution when we validate, right, our system between short circuit and dynamic stability using the utility only. So let's just open them. Let's just close them now and see if I add certain parameters to the generator and motor regarding stability model, would the result be the same? Which one makes more sense, etc. Right? Add dynamic model, add motor model, close the breaker and open the breaker main. We already did that. We close the breaker generator feeder and we open the breaker main feeder. So my system is fed by the generator, but not the utility, not by main, right? Then we go to DS focus. We enable arc flash and choose the IEEE 1584 2018 method and double click on the MC16. I have to be honest, I forgot how to get this result. Let's try. But again, the practice is to show that how we can get this result and how the result will change. So let's just give this a try and say what stability model should be used to get the arc flash energy, arc flash time, arc flash boundary. Those results, the purpose they are here is because I want to show you that those results here should be totally different from the arc flash calculation that we enable them and use the short circuit impedance to get. Remember, you can have different set of dynamic stability results, right? If different model will be selected, but you can have only one set of short circuit focus based arc flash result. That's the purpose of what we're doing here, is to show that for this one set of short circuit results, we depends on different dynamic stability model we have for the generator and the motor. This result can be totally different. And that comes to our judgment, engineering judgment of what is the right result to use, what is the most conservative design we have to stick to when we work on the system, right? So let's just take the DS example and DS example -1 easy as an example. There are too many examples here, right? So still no questions, which is good. So let's go back here, open the breaker, close the breaker to have both the generator and motor contribute to the bus fault. Is that all? Let's just double check. Impedance. Oh, I do have my X double prime D, I do have my X prime D, and I do have my X0 zero sequence here. Okay, which is good. Motor. Short circuits. I do have my lock rotor impedance, right? So I have enough data for me to calculate arc flash in short circuit focus. Double click, that's the result, right? Let me just check if it is consistent with the result I got before. It is consistent. This means that no matter how you change your parameters, right, as long as the configuration is consistent, nothing changed, the result should be consistent, which is a good information, right? 105.8 arc flash boundary, 19.3 arc flash energy, incident energy. Okay, consistent result here. So let's go back. By the way, you cannot go to stability now. Even if you do, there is no stability model for this generator and the motor. So there is barely any difference regarding the short circuit calculation, right? Just double click, you will see that it's pretty much the straight line. That's not what we want to see here, because what we want to see here is some curvy, some continuous changing current instead of a straight line, right? And let's just go back to database edit just to add the stability model to it. Again, I have not validated any of the stability models, just okay, here's a question come in. Thanks for the session. Currently, we are using arc flash calculation with focus on short circuit, not BS. Going forward, how we need to do that? I will follow up with that question later. That's not a question we can answer through the webinar. Again, feel free to ask questions. If the question takes more time, like just this question that I'm reading, I will just follow up with you. Maybe Jim can follow up with you as well to go over your needs, right? So let's just enable the generator model. Make it simple, right? Generic model, round rotor, standard round rotor. And click on import library. So all the parameters will be imported. Again, I don't validate all the parameters. Those parameters do not use the standard library you imported from EasyPower, please. It's not accurate at all. It's just an example to show that at least this works. That does not cause any initialization problems for the generator. When you perform a real system study, always fill out every parameter according to the manufacturer provided data sheet. Okay. I'm gonna enable the excitation model as well, because excitation system model, exciter model, is the most important model to determine how much fault current the generator can produce, right? So let's just use a plug-in model. I'm gonna first start with a static exciter, which is the fastest excitation system, right? We have three types of excitation system, remember? DC excitation system, which is very old, almost does not exist in the market. We have AC excitation system, which use alternate current as your excitation system, right? Which is faster, widely used. And at last, we have the static excitation system, which is used in those power electronic devices, which is extremely fast and extremely powerful, but maybe more expensive or to implement in your system. So we are going to use the most, I would say, the most responsive excitation system, for example. Then we will switch back to DC excitation system and say, what's the difference, right? Click on OK. Well, now the generator symbol becomes a shaft with some circuit, right? That means you have dynamic stability model for the generator. We also do the same thing to the motor. Go to dynamic stability, enable motor model. The same thing here. EasyPower does provide you a set of standard induction motor model. Do not trust any of the parameter at all in your system. Always ask your manufacturer of the motor about what parameter to be used. Okay. Override power factor and efficiency, it doesn't matter, right? So I don't need starting load because I'm not doing any motor starting study. I may not need motor running load as well, as this is not I would say a frequency dependent study, it's just a fault study. The item data is not complete. Do you still want to commit the data log? Fine. Make it happy. Just use generic standard. Okay, generic standard cubicle. Okay, so now it does not complain. The program does not complain. And let's go to dynamic stability. Same story. Make sure that we have BS options. Make sure the arc flash is enabled. Double click this bus. Now you can see that I have a fault here, and my excitation system immediately boosts my excitation current, right, to restore the voltage. Of course, it cannot restore because you have a fault in the system, right? But it tries its best to regulate the voltage. So in this case, let's take a snapshot of this. What we care about from the log file, I care about my arc flash energy. I care about my arc flash time. I care about my arc flash boundary. If you really want to get into the details, okay, I have my trip time. I have my breaker open time. And those are the relay information for other relays does not trip the device, but we have the relay trip the device, right? Now let's come back to short circuit. If I double click this, open the arc flash, you will see that, first of all, let's look at the big picture, okay? 19.1 as my arc flash energy. I got 19.3, not too bad, right? Arc flash boundary, 104.8, 105.8, not too bad either, which means that if I use the static excitation system, I can mimic my arcing currents and my relay performance close to each other. The upstream device tripped is RGen, is this relay here. So the generator tripped, but not the overcurrent relay of the bus tripped, right? So you got a similar arcing time, 0.972, 0.927, right? You got a similar arc flash energy, you got a similar arc flash boundary. Okay, life is good. I got close enough result to show that if I use static exciter, my short circuit result is consistent with my DS result, even considering the dynamic performance of the system, right? Let's go back to dynamic stability and do it again. Look at the curve that you can see, okay, the current is somehow around this level. That's your arcing current because you have a fast excitation system. So you can mimic the triangle, some sort of triangle, right? Instead of the rectangle here. That's your incident energy calculation. Now let's do another experiment. What if I do not have the luxury static excitation system? What if I have a, let's say, very old school DC excitation system? Do we even have a DC? We do. We have a lot of DC excitation system model, and I'm gonna go with DC4B. It's one type of DC excitation system, which I believe, let me make it slower, right? Which I believe is much slower than the static excitation system. So we'll see how their fault current looks like during the dynamic stability simulation, and how will that affect our short circuit and arc flash calculation results in dynamic stability. Everything is the same. I didn't change any configuration at all. All I've changed is the excitation system. Now I'm gonna double click this. Oops, you'll never be able to clear the fault within the simulation. Why? Because your current, instead of going up, the current goes down, right? So you have a lot of much larger arc flash energy. You have much less fault current. Remember, the fault current goes up after the fault applied, right? Just now for the excitation systems, for the static excitation system, because of the large fault current, the relay can operate properly. In this case, the relay will never clear. And you will always have this fault current going on, which extends to the end of the 6-second simulation. If you set the 6 seconds to, let's say, 100 seconds, that will be even worse, right? So the arc flash energy is extremely much larger than what we have had before. 19.1, now it's double, more than double, right? Arc flash time becomes 5 seconds, remember, because our time, the total time of the simulation is 6 seconds. So the arc flash time goes from wherever the fault started all the way to the end of the simulation. It never gets cleared. That's exactly is happening if you really have a slow DC excitation system. And it will have a lot of arc flash energy, and the arc flash boundary is extremely large, right? So this is the impact of the dynamic stability model to the arc flash calculation. And to be more realistic, let's say if I use AC excitation system, let's say I'm going to use let's AC11C, which is most accurate, the latest HB 421 standard. I believe we developed this model according to the standard based on the customer request, right? If I use a decent sized or decent, I would say fast excitation system, slower than static, but faster than DC, what will happen? Go to dynamic stability, double click. Okay, it does strip, right? The arc flash energy reduced. Remember, short circuit gives about 19, and the total arc flash boundary is 105, something like that. And now, because of the excitation system change, your arc flash energy becomes only 17.9, right? Your arc flash time is slightly longer, but because the current has been limited, instead of going up, it goes down, but it does not go down like DC excitation system. So your dynamic stability evaluated arc flash is less severe than what the short circuit gave you, with different dynamic response of your system equipment. Your arc flash energy can go up, can go down, can be close enough to your short circuit focus, calculated arc flash energy, right? Arc flash result. So those are what we want to discuss and focus on as of today in today's webinar. Any questions?
Tao, so where does it show that the arc was cleared on the log?
Yes, the arc cleared on the log is here. So if you read the log file, 1 second, fault started, right? Mm-hmm. 1.0017, that's where the relay pick up on those two relays. At time equal to 1.965, that's where the relay tripped on overcurrent. At time equal to 2.0492, relay aux time, breaking clearing time satisfied, and then the breaker opened. This is the breaker time to open, and 2.0492 is the breaker opening time. That's why your arc flash time is 1.193 seconds, which is this value.
Yeah.
Right?
Yeah.
And if you use arc flash time minus when the fault is applied, then your real I'm sorry, when your real arc flash time would be 1.193, because at time equal to 2.0492, that's where your breaker started, right?
You do have a question.
Is the exciter data usually included in the generator nameplate? No, the exciter and the generator are usually from different manufacturers. Because if you buy a generator, right, you can buy it from GE, you can buy it from Siemens, you can buy it from ABB, whatsoever. Exciter, you can buy it from, let's say, Drexel, right? Or Dexel, I'm sorry, Dexel in Illinois. That's the exciter we worked before. You can buy it from ABB as well, right? You can hook up your ABB Unitron 1000 with your GE generator as well. There is nothing stop you as long as they mutually have the capability to operate against each other, right? So usually the excitation, especially the automatic voltage regulator, comes from the exciter manufacturer. However, the amplitude of the excitation system is usually equipped with the generator manufacturer. So you have to obtain data from both the generator manufacturer and your excitation system manufacturer. Any other questions? Does that make sense, Frank?
That was very good.
Yeah. Okay. Thank you, Frank.
Thank you, Tao. I'm going to take the screen back. Thank you all for attending today. Just a reminder, we do have Arc Flash resource material on the website, and each month we do an Arc Flash workshop. So those are all free of charge, and you're welcome to attend at any time. Thank you for attending, and we'll be talking to you down the road in other webinars. Have a good day.